Hi and welcome back to a new video. Well, last video pretty much exploded where we were reporting about this RTX 5090 Founders Edition having a very uneven load and current distribution across this Corsair 12-volt high power cable, resulting to one of the wire having 22 to 23 amps and then resulting in the PSU connection quickly reaching up to 150 degrees Celsius. And of course, there are a lot of questions about these topics, a lot of comments, also some critique I want to reply to. And I can still already spoiler, yes, the 22 amps were real. This video is brought to you by the Endorfy Navis AIOs, which are now available at a significantly lower price than before. For example, you can get the simple Navis F240 starting at $59.90 and the powerful F360 ARGB starting at $89.90. With a quiet pump featuring a ceramic bearing and pre-installed fluctus fans, the price-performance ratio is outstanding. You can find all the details in the link in the description. To quickly recap the situation. I was testing my RTX 5090 Founders Edition that I transitioned to custom water cooling. And while testing, I noticed that two of the wires of this Corsair 12-volt high power cable were unusually warm. Then after touching this, I noticed, well, this can't be right. I got out a thermal imaging camera, which is a PeakTech 5620. This is not a toy. It costs about 3,000 euros and is also calibrated. And also you can set the emission factor accordingly. There's a manual which states exactly what kind of emission factor you have to use for which surfaces. And I also double checked the surfaces to get a reference, as you could see in the previous video. For example, we knew the water temperature was about 22 degrees Celsius. We were pointing it across the water cooling connector. We could also see roughly 22 degrees Celsius. You can also double check this by looking at my skin temperature of my hand, which was in the mid 30s. So this all aligns. And if you're now thinking, okay, your thermal imaging camera might be off by 10%, maybe 20%. Well, even if it was off by 20%, if we are looking at a connector temperature of 150 degrees Celsius and it was off by 20%, we would still look at 120 degrees Celsius, which would still be too warm. So that argument is just completely invalid. Before we get to the current clamp, I want to highlight again that the issue I was showing in my previous video was about this very specific cable, this single cable, and this specific GPU in combination. I never said that this is with every 12-volt high power cable or every Corsair cable or every 5090 Founders Edition. I'm not sure why a lot of people think that, but that's literally nothing I ever said. It was about evaluating Ivan's case, where we saw that one cable was melting, which meant that there has to be a high current flowing across a single wire. And then it was just coincidence that I had a very similar case of a very uneven current distribution on this wire, and that is probably the same kind of thing. It was just to show that there is nothing that holds a cable like this back from having exactly this technical scenario, which could eventually lead to the failure that, for example, Ivan was saying. I saw a lot of other tech media trying to replicate what I was seeing, and I'm absolutely not surprised that pretty much nobody could replicate this. This makes absolute sense. If you just go back 2 years in time, think of the RTX 40 series. We had exactly the same scenario. We saw the single cases of melting connectors, and we saw almost all the media jump on it, try to replicate the issue. A lot of media has tried it, even with like trying, overclocking, cutting wires and everything. And even then, it was usually impossible to try to get the connector to melt. For example, also Gamers Nexus spent a lot of time. I mean, they have brilliant videos about this topic. You should maybe watch again, because sometimes it feels like we're just repeating the same thing over and over again. What he eventually found was one of the problems, not the problem that causes everything, right? But what he found was if you don't plug it fully in, then it can cause the connector to melt. But that was just one of the scenarios that can happen, and he made it clear. A prime example can also be seen by the testing results published by HardwareLux, where Andreas Schilling was testing with his 5090 Founders Edition. He put it on load, and on the first test, pin 1 was pulling 3 amps and pin 5 was pulling 10 amps. So he also saw an unusual power distribution. It was just not as bad or as big as in my case, but then, just plugging the same connector again, it was suddenly 7 amps and 8 amps between the pins. Jay also tested this behavior in his current video, and he verified this with an RTX 5090 from Zotac, and he also could find an uneven current distribution. Again, not as bad as in my case, but as you can see, 3 out of the 6 pins were running outside of the spec of max 9.5 amps, which just shouldn't be the case.
Whoa. 7.8, 7.9, 8, okay, not terrible. 6.2, 12.1, 10.5, 7.9, 10.7.
So not as bad as Verbauer's, but still pretty inconsistent.
And while the problem in his case was much smaller than what I was seeing, it just highlights exactly the same behavior of you plug the connector and you have pin 1 here, have 3 amps under load, and then you just plug it again and suddenly you have 8 amps on pin 1. That is more than 200% difference between just plugging the same connector twice. And that is just exactly what I mean, which is concerning. And also that one of his pins was showing 10 amps, while the card was pulling 530 watts. That is not the max. The card can do 575 watts, right? So it would have gone maybe to, I don't know, 10.5 or 11 amps. But even 10 amps is already out of spec for the connector, because the connector is rated to 9.5 amps. So even in his very simple case, it was also already running out of spec. Buildzoid made a brilliant YouTube video where he was showing why the entire problem with the melting connectors basically started with the RTX 40 Gen. I highly recommend that you're going to watch this. The summary of this is that RTX 40 and RTX 50 cards have no way to tell how much current is flowing across which of the pins. If you're just looking back to older cards, maybe RTX 20 Gen or 10th Gen, or even a recent AMD 7900 XTX, these cards can sense the current at least per connector. And if you have, for example, 3 connectors, you would have 3 inputs. Or for example, also on a 3090 Ti, the 12-volt high power is split into 3 inputs. And those 3 inputs can then be load balanced, which means that at least the 12-volt high power connector would be divided by 3, which means you can load balance between those 3 pins. But all of this is not possible with RTX 40 or RTX 50. The Asus Astral cards, they have advanced monitoring, which allows them to monitor the current across of the 6 pins, but it doesn't allow them to control it. It's better, but it doesn't solve the problem. Now going back to my previous video where I was showing 20 amps, above 20 amps flowing across one of the wires. And I can't even recall how many times I read, even from like professional guys like Aris or Johnny Guru, that 20 amps across one of the cables would be impossible.
So we made a video yesterday explaining why we believe that it is impossible to have 23 amps on a thin cable AWG16.
Which it obviously isn't. So we will talk about the current clamp in a second. Luckily, the 12-volt high power standard is so stupid that it's extremely easy to replicate this. We're looking again at the 12-volt high power cable, this time 90-degree angled, which doesn't matter at all. In general, this cable has 14 pins. 6 big wires on the bottom, those are the ground wires. We have 2 small ones, which are the sense pins or sense wires, and then we would have another 6 wires for 12-volt, but as you can see, I cut 4 of them. So 4 of the 12-volt high power cables are cut, so the entire load for 12-volt current will just go across those cables. They're not soldered together or anything, they're just taped together so I don't mix them up. Now, if you're not too deep into the topic, you might think that you can't just cut wires, like the GPU wouldn't start, right? Well, the thing is, you have those sense wires, and if you translate or if you're looking at the word sensing, you might assume that it's measuring anything. Or, yeah, I mean, they're saying that it's sensing if the connector is plugged, which is not really true. The only thing that the sense wires are sensing is that the sense pins themselves are sensing something. So they're just sensing themselves, nothing else. So you can assume that the plastic housing is in the same position as the sense pins, but already that is an assumption. But it wouldn't detect if any of the other pins wouldn't make contact or bad contact. Nothing of this is checked or measured. So the sense pins are just sensing themselves and are probably senseless. So we're just starting the system. The setup is running. You can see the 4 cut wires, just connected them. Those are PSU side, and GPU, you can see 4 wires of 12-volt supply being cut. Now if we go over to hardware info, which I already opened, this is currently idle. So we see somewhat between, I usually see lowest maybe 12 watts and in idle maybe 30 watts power draw, which then divided by the 12 volt power supply should be something between 1 and just below 3 amps. Now the current clamp, we should measure something, as I said, about 3 amps. I would say, yeah, that is pretty much spot on. Obviously some fluctuation, but pretty accurate around 3 amps. Now just to double check everything, we have a second current clamp, which is not as easy to look at, but it's also very accurate and a nice thing to use actually. It is just translating the current into a voltage. So what we're measuring here, we can set that it is giving us 1 millivolt per 100 milliamps. We are trying to measure 3 amps, which is 3000 milliamps. That means we should get 30 millivolts if we're just looking at this scale. And for that, we just have to use a multimeter. It's set to millivolt DC current, DC voltage. And if we're now hooking this up to our 12 volt supply, yeah, it's 33 millivolts, but that would equal 3.3 amps. I mean, something might happen in the background, but you can see it's pretty much in line. That was just to show that this current clamp is not reading nonsense. It is reading the same as the second current clamp. It also aligns with what we can see in hardware info. I'm always double checking things like this. And what we will do now is we will fire up the card with Thermic again. Keep in mind, we cut 4 of the 6 12 volt supply wires. The card will pull 575 watts, which if you divide it by the 12 volt is something around, I don't know, 49 amps. 49 amps that should flow across those two 12 volt wires. We're now starting up Thermic. You can see it instantly jumps to 50 amps. 2 wires. I'm touching the wires. They're not instantly going up in flames. I'm not burning my fingers because this is, I don't know, 40, 50 degrees Celsius, something in that direction. And you have to keep in mind that this is 2 wires, which means that we should have maybe 25 amps across an individual wire. But I read the comments that this is physically impossible. I would burn my fingers. This would instantly go up in flames. It would instantly melt the cables. As you can see, it doesn't instantly melt the cable. It also doesn't melt my fingers. I can get the camera probably out to get the temperature. It feels very similar to what we had in the previous video. So just checking individual wires to prove again, it is possible. You're not burning your fingers. It's not going up in flames. You see it. It's 25 amps on one of the wires. And I mean, it's a new cable and it also looks pretty decent, I would say. Like there's no imbalance on this cable, which is great. And again, you can see 25 amps. Checking this, 50 amps. We're now filming off the screen of the thermal imaging cameras. You can see this is exactly what we're filming. And obviously the wires are now carrying about 2 to 3 amps more than last time, so it's expected that it's maybe 5 to 10 degrees Celsius warmer. But again, you see also, yeah, it is roughly 50 degrees. I can touch it. You can see how I touched it, how this area is then colder. Yeah. This just validates again what we were seeing in the last video, where we could see a very uneven power distribution across this cable, where you saw most of the current flowing across 2 cables. Those were lighting up under the thermal imaging camera, roughly the same temperature. This time it was a bit warmer, simply because we were just pulling all the current across only 2 wires, where here we could still see some current across the rest of the wires, maybe 2 amps or 6 amps. But now the extreme case, even with 2 wires, it is not instantly going up in flames, as I had to read. You can still touch it. Obviously, I was still, again, running it for maybe 5 minutes. Again, same as in the last video. Also in the last video, I said it's absolutely not recommended to run this for, I don't know, like an hour under load. Something will definitely fail eventually, but it's not happening instantly. And all of this very uneven current distribution on the cable, which technically should not happen, but it does, it can happen, as you could see in my case, is only possible of the combination of this connector and the design of what Nvidia is going for with RTX 40 and RTX 50. I obviously also ordered new cables, which we will just try, and I would assume that with this cable, it should be fine, hopefully. Firmware is running again, just going through the wires. 8.5 roughly, 8.3, 8.3, 8.1, 8.2, and 8.3 again. Going back to the initial problem, and that was what my initial video was to showcase. You know, we were investigating Ivan's problem, where we saw that one cable melted, which definitely indicated that there was a very uneven load distribution across the 12-volt high power cable with the 6 12-volt lines. And I assume that most of the current was flowing across one of the lines with his case. And it was a similar scenario that we were seeing on this probably faulty cable. And the thing is that here it was not bad enough. You know, we saw a very uneven power distribution with 2 lines carrying 20 amps, 22 amps, which was bad. Not bad enough to instantly make it melt like with Ivan's case, but it is to showcase the entire problem, like the bigger picture, which is that the card just has no clue if the 50 amps that are flowing in total are going across one of the wires or across all of the 6 wires, and in which way they are distributed within those wires. It is a very sensitive system that is running on the edge. And whenever anything in this system fails, that could be some kind of contact resistance, that can be some kind of manufacturing tolerance. If anything of this in this sensitive system fails, then it's doomed. I also read some comments that I should have already tested this in the first video, you know, retesting with a non-faulty or good working cable to double check that, which I can understand, and I can also agree to this critique. I also still want to highlight that it's not the point about finding a working cable. It's about highlighting how easy the system can fail. And that what we sometimes call, or what, I don't know, a lot of users often call simply a user error, might not essentially always be a user error, and that the system itself is just the problem. The system itself allows those issues. And it would actually be quite easy for Nvidia to change the design that none of these issues would even be possible. There is also a good read I can recommend from an Intel engineer on Reddit that is talking about the connector and the entire system, and also how bad it is designed in terms of safety margin, which is non-existing. And it's funny because he's reporting exactly the same values, exactly the same problem that we already highlighted exactly 1 year ago when we did our big 12-volt high power critique video, where I was also mentioning the non-existing safety factor of only 1.1, whereas with the older 8-pin connector it was at least 1.9. The point of these videos is to force Nvidia to change the design. We know that Nvidia is capable of making good designs if they want to. If you look back at the 3090 Ti, it didn't have the issues. It had a monitoring and also a load balancing. Now if we look at the RTX 4090, and this is what makes me in particular mad, we saw the issues with the 4090. We saw burning connectors. We had all the drama. And then instead of learning from the entire situation, we just made things worse. Instead of fixing anything, instead of giving this at least split up the monitoring by 3, no, we increased the power draw by 28% to the 5090. And that is something I just can't understand. And if you're an engineer, and if you look at this topic as a whole, you can't tell me that you think this is a good idea to do so. You just can't tell me that this is fine to do so, especially with the non-existing safety factor. And my case from last week was to clarify that these technical issues exist. It was to highlight Ivan's case and to show that what he was experiencing might exist more. And it is technically possible. And it should not be technically possible. It would be easy to fix for Nvidia. If they would go back to the 3090 Ti kind of power delivery design, we would not be here. We would not have those discussions, and we would not see those issues. Because the biggest problem for me is that, you know, once in a while we see the melted connectors, and then I see always it's a user error. User error again. The cable was not plugged in again. And are we sure about that? Or should the design just be that you plug it and it works, and there are safety features that just prevent this from happening in the first place? You know, the safety factor of 1.1 itself is already a joke. And having a safety factor of 1.1 without any kind of real measuring is an even bigger joke. You know, Nvidia, if you were to measure every single current pin on the cable, if you would measure all the 6 12-volt pins and check that everything is working fine, you know, you're checking it by software, whatever kind of safety measures you would imply, with load balancing, then you could maybe argue that the safety factor of 1.1 is enough because you're double checking everything, yeah. But not checking everything and having a non-existing safety margin of 1.1 is just not good. It's not sufficient. And every engineer will tell you that this is not a good plan to do so. And I'm fine to listen to another 50 "this is clickbait" comments, but if we manage to, you know, get Nvidia to change the design, then we achieve exactly what I want to achieve, because in the end, everyone will profit. We would be sure that nothing melts. Nvidia, we wouldn't have to do those videos again, which are hurting everyone. It's hurting me, it's the consumer, it's hurting you. It would just be simple. Just fix the design and we can finally stop talking about this. All right, we will still do a follow-up because I still want to test more stuff about this cable, the broken one, probably broken one. And, you know, I don't know, plug it 100 times and see what happens and check resistances and all that. All right, so much about the follow-up. Thanks for tuning in. See you next time. Bye-bye.